Okay, guys, so welcome back. Well, not like welcome back because we don't really leave the screen nowadays. But anyway, we are going to talk about geologic time. So this will be part two, the second video for this particular module. Now, these are the key questions that we want to try to understand with this module, and that will actually be focusing on what is the geologic timescale and what are the different principles that govern the GTS. And of course, how do we determine absolute age and what are the different geologic time periods? So those are the ones that we want to focus on for this one. But first, let's recall a little bit of principles about your relative age dating, which was covered in the previous video. Now, when it comes to relative age dating, we try to use the principles of stratigraphy, wherein we try to relate the different layers to each other, and then eventually determine which is older or younger relative to each layer. So again, this particular method tells the story of which came first, but not exactly the specific ages. So we don't really get numbers from any of this when we use relative age dating. But when it comes to absolute age dating, we actually get an estimate, an accurate estimate of the age of the geological material. When we say geological material, we may mean the rock or a fossil of some sort, or even ancient artifacts. So we actually get to determine the exact age of these objects now, and that we usually utilize isotopic or radiometric dating. So here we try to use or manipulate uh, how the decay of radioactive materials can help us tell the age of an object. So, just a little fun fact for all of you before we go into this. This is the Shroud of Turin. The Shroud of Turin is an ancient artifact that is said to have wrapped around the body of Jesus as he was being laid to rest. Now, if you can see right here, you can see the picture of a man. Now, in this case, they say that this has actually touched the earthly body of Jesus Christ himself. However, carbon 14 dating tests around 1988 has revealed that the age of the cloth to be 1260 to 1390. So in this case, this was way past the time of Jesus Christ. So therefore, this must have been a replica made around the medieval ages. So why do they make medieval why do they make these kinds of materials? Well, they sell for a lot of money, of course. So that's usually the motivation for these kinds of materials. But the Shroud of Turin is said to have been a fake artifact. Fun fact, not so fun fact, I guess. Now let's go back to isotope dating. When we talk about isotope dating, we're talking about how we utilize the half-life. The half-life is actually the constant rate of spontaneous decay of the radioactive materials. So we use that to measure the age of the material. So the half-life is the amount of time it takes for one half of the amount of the radioactive material to decay to its stable isotope. So I know it sounds funky in your mind right now, but we're going to go through the different basics so you can understand it better, okay? So when it comes to that, there are different isotopes that we know, and that at the same time, these isotopes are actually found in different rock formations. They are actually found in magma or even deposition of sedimentary rocks. And that we actually utilize the precise measurements of the ratio of the production of the daughter isotope from the parent isotope to determine the number of half-lives. And eventually, by determining the number of half-lives, we eventually come up with the age of the material. So this photo right here would actually try to show us as to how with every number of half-lives, the parent material, the parent isotope, eventually turns, the parent isotope in yellow, eventually turns into the daughter isotope or the daughter product. And that as time passes on, less of the parent material exists and more of the daughter material actually comes into existence. So we usually use that ratio to determine the age of the actual object that or rather the actual sample that we're looking at. Of course, it depends on the object as to which isotope we're going to use. Different objects would oftentimes have different isotopes that would be more appropriate for them. So these are the different these are rather the common isotopes when it comes to radiometric dating. So we have carbon 14, and carbon 14 here is the, sorry, natakpan siya. Carbon 14 is the parent isotope. Eventually, the daughter isotope is actually nitrogen. So for every half-life, yung carbon nagiging nitrogen. So and that, what usually carbon turns into nitrogen in every 5,730 years for this particular isotope. The same relationship can be said for rubidium 87 turning into strontium 87, potassium 40 turning into argon 40, and the other ones. And if you would notice, carbon 14 rather, is actually the one with the shortest half-life in this case, and that it's actually oftentimes utilized for fossils. But at the same time, syempre, for older fossils, um, there are better isotopes to be used. So here's an example of a dating problem. And when we say dating problems, we don't actually mean people. We actually mean rocks. Maybe rocks are better than people. Ayan. So here we have a fossil sample containing 150 units of carbon 14 and 1050 units of N14. So here we can notice as to there's a relationship between the parent isotope and the daughter isotope. Now we are being asked as to how old is the fossil. So we first get the number of initial carbon 14. So we get the initial amount first. So before they became N14, they were actually carbon 14 first. So we add those two together to get 1,200. Afterwards, to determine the number of half-lives, we actually divide this by 2 raised to h, and we get 150. Now, the next part is to solve for h, and you can actually use that. You can actually compute for h by using your log in your calculator, by using negative log. Basta yung log function sa calculators nyo, you'll eventually have 3 for the number of half-lives. So with that, how do you now determine the age of the fossil? You have to go back to the half-life, to the actual half-life of your carbon-14 isotope. It's actually 5.7 times 10 raised to the 3 years, or 5,730 years. So with that, we simply multiply the number of half-lives to the given half-life of the isotope, which is carbon-14, and eventually we come up with the age, which is 17,100 years. It's a 17,100-year-old fossil. So when it comes to your worksheets, there will be a couple of problems that look like this, but we're actually going to use a simulator from PhET to actually help you with your dating problems on rocks, not on people, okay? So moving on, the Earth is actually 4.6 billion years old. How do we know that? Again, the rocks will tell us a story about how old the Earth actually is. So with that, how do we know about the history of the Earth? We usually utilize the geologic time scale. Now, this time scale was brought forth based on geochronological data. Geo meaning Earth, chronos meaning time. So in this case, we came up with data based on what rocks would tell us. Like rocks can actually tell you about volcanic eruptions, earthquakes, and whatnot. There's a lot to history as to what the rocks will tell us. And of course, there have been isotopic and relative dating rock records as well. And that the Earth's 4.6 billion year old history can be divided into periods with specific periods of time. So with that, let's talk a little bit more about your time scale. So the naming of the units are actually arbitrary. When we say arbitrary, it does not necessarily mean that the the terms are actually named by man. So medyo subjective yung ways as to how they are named. For example, we have Cretaceous period. You would expect that the Cretaceous period is chalky, but no, not exactly. We have also Devonian, which is an English country of, of Devon, but it has nothing to do with the actual period, and so on and so forth. So this is actually what it looks like. It's divided into eons, eras, periods, and epochs. And what do you notice? What is the biggest division? So your biggest division is eons. What's the next one? Eras, periods, and eventually the smallest one is your epochs. So in this case, that's how it's divided, in that there are certain events or certain happenings that are actually notable in each eon, era, or period. And that oftentimes there are a lot of images that will actually tell us a story. So, for example, during the Proterozoic era, it's actually no, this is actually like the first birth of different algae, and also microbial life, and that most life actually exploded during the Cambrian period in the Paleozoic era. And of course, one notable extinction is that what happened in the Cretaceous period in the Mesozoic era. That's actually when dinosaurs started to die out. Now, more of this time scale, like the actual happenings, will actually be discussed in a short documentary that is attached in the with this particular video as well. So there's a short documentary from PBS that will further discuss the happenings in the geologic time scale. So furthermore, eons represent the greatest expanse of time. So show you the largest division of time here. Eons are eventually divided into eras. Eras are eventually divided into periods. And finally, periods are further subdivided into epochs. So just a bit more information. You can actually go through the slides and eventually check out what are the different divisions here. So your Phanerozoic eon is actually divided into three eras: Paleozoic, Paleo meaning ancient life, Mesozoic, Meso meaning middle, and then Cenozoic meaning recent life. So when we say Paleozoic era, it's prehistoric. So here we see the most primitive organisms, rather more primitive multicellular organisms, because before the Paleozoic era, there were actually living organisms, but chances are they were microbial, they were single celled. We also have the Mesozoic era, and here we can actually find the age of the dinosaurs and the rise of the mammals, the reptiles, and the fishes. We also have your Cenozoic era, which is more of the age of your mammals and your birds, because when dinosaurs started to die out, mammals actually started to thrive because there were less predators to hunt them down. And that actually, the Grand Canyon, the layers of the Grand Canyon actually date back to the Precambrian periods, or the Precambrian era. So eventually, all the rocks actually tell a story. And that one good example of a historic rock is actually your Grand Canyon. So right now, what epoch are we actually living in? We're actually living in a proposed epoch, which is the Anthropocene. This actually means human and new and recent. And this is actually characterized by heavy technological advancements from people. And of course, this is due to the significant effect of humans on the Earth's geology and eventually the ecosystem, brought about by our activities, be it good or bad, but mostly bad. So hopefully, as we end this video, you'll take the time to watch the PBS short documentary after this, and that you'll get to learn more about your geologic timescale based on the activities that we have provided for you. So don't be afraid to try out the practice worksheets, and don't be afraid to ask for help if you need it. If ever, I guess this is my last video for this particular subject, and that I'll see you when I see you, Luke 21. Bye bye. Peace.